Have you ever wondered how a self-driving car actually knows a pedestrian is about to step into the street? Or how a digital avatar perfectly mimics your every single move in real time? Well, welcome to this explainer. Today, we're diving into a genuinely fascinating computer vision problem called pose estimation. We are going to demystify exactly how artificial intelligence sees and interprets human movement. But hey, before we can even begin to map out a pose, we have to ask ourselves, how do we mathematically define the human structure in the first place? I mean, we can't just tell a computer, hey, look for a person, right? We need a really strict numerical framework, something that translates the insane biomechanical complexity of the human body into pure data that our machine learning model can actually understand and process. So here's our roadmap for today's explainer. We're going to start with understanding pose estimation, then look at real-world applications. After that, we'll journey through the pre-deep learning era, enter deep learning, explore the heat map revolution, and finally, wrap up with tackling multi-person poses. Let's jump right in. Section 1. Understanding pose estimation, the foundations of the body. So the absolutely crucial point here is that pose estimation is all about predicting a set of specific coordinates. We call these key points, and we use them to map out the body. Honestly, it's kind of like a highly advanced digital game of connect the dots. The system's goal is to ingest an image and spit out specific X and Y pixel coordinates for vital joints. We're talking about finding the exact locations of your wrists, elbows, shoulders, hips, knees, and even facial features like your eyes and ears. Now, notice how the complexity scales up depending on the environment. At level 1, we're really just looking for 2D points on a single isolated person. Pretty straightforward, right? But level 2 ramps it up to crowds, detecting and grouping key points for multiple people all at once. And then there's level 3. This introduces the massive challenge of 3D full-body estimation, where we actually have to recover depth, or the z-axis. This is incredibly difficult because of something called depth ambiguity. Basically, a 2D image is just a flat projection, meaning multiple different 3D poses could theoretically look absolutely identical from the camera's single perspective. And that brings us to the core anchor for our entire explainer, treating the human body as a graph based on the 17-point COCO standard. What you're seeing here is exactly that. The nodes are the 17 anatomical joints, and the edges are the skeletal limbs connecting them. You might be wondering, why a graph? Well, it all comes down to structural reasoning. Joint locations are interdependent. If the computer finds your shoulder, anatomical constraints mean your elbow can only be within a certain distance. Treating the body as a graph basically prevents the AI from predicting completely impossible, logic-defining body contortions. Moving on to Section 2, real-world applications, and why tracking actually matters. The real-world impact here is absolutely massive, and it shapes our daily lives way more than you might realize. In healthcare, it's being used for clinical gait analysis and automated fall detection for the elderly. In sports analytics, it gives athletes instant automated technique correction. Autonomous driving relies heavily on this to predict pedestrian-intended crosswalks, which is literally saving lives just by understanding body language. And in entertainment, it's completely revolutionizing motion capture for animation and gesture-based controls for AR and VR. All right, let's step back in time for Section 3, the pre-deep learning era, looking at springs and templates. We've definitely evolved from some mathematically elegant but honestly highly brittle systems. In the pre-deep learning era, engineers relied on handcrafted templates. They'd model body parts and connect them with metaphorical springs. The system would evaluate a patch of pixels and apply a deformation cost if the joint strayed too far from normal anatomy. But man, it was incredibly fragile. If someone's arm was hidden by a jacket, a situation engineers call an occlusion, that virtual spring would snap to a completely wrong guess. This limitation pushed us straight into the early deep learning era, where models like DeepPose abandoned those handcrafted filters, used convolutional neural networks, and just tried to directly regress, or guess, the exact X and Y coordinates. Which brings us to Section 4, Enter Deep Learning and the Coordinate Flaw. So DeepPose treated this whole thing like a standard math problem. You feed it an image, and a fully connected layer spits out a number for the X coordinate and a number for the Y coordinate. But there is a massive limitation with direct regression here. By passing the image through fully connected layers, the network fundamentally loses the spatial layout of the image itself. And because of that lost spatial awareness, a tiny microscopic numerical error in the math translates into a massive, wild displacement of pixels on the screen, totally missing the joint. It's a huge flaw. To fix that, we get Section 5, the heat map revolution, visualizing probability. This was a real game changer. Instead of guessing an exact coordinate number, the network now outputs a heat map. Think of it like a weather map, but for probabilities. The network generates a 2D spatial map for every single key point. A pixel on this map lights up bright red, meaning high heat, if the network is super confident the joint is there, and it fades out smoothly based on its uncertainty. The final predicted location is just the single pixel with the maximum heat value. This beautifully and elegantly preserves the local spatial structure that the older models lost. To actually generate these heat maps effectively, researchers developed a famous architecture called the stacked hourglass network. It uses this brilliant three-step process. First, the encoder works bottom-up, downsampling the image to zoom out and capture the global context. Things like the overall orientation of the body. Then the decoder works top-down, upsampling back to normal size to recover spatial precision. Crucially, though, it uses skip connections to preserve the fine-grained details that might have gotten blurred out. And why is it called stacked? Because it repeats this entire hourglass process over and over, iteratively refining the heat map with each pass until the prediction is incredibly sharp.
All right, Section 6, tackling multi-person poses, moving from top-down to bottom-up.
So, the traditional method was what we call top-down. You'd find every person first, draw a bounding box around them, and then estimate the pose. But you can imagine that gets incredibly slow if there are 50 people on the screen. Instead, the open pose architecture introduced a bottom-up pipeline. First, it extracts visual features using a powerful foundational model called a VGG19 backbone. Then, a two-branch system simultaneously predicts heat maps for every single joint on the screen and predicts the limbs. Finally, it uses a matching process called the Hungarian algorithm to match and group those joints. This is huge because it means the processing time is completely independent of how many people are actually in the crowd. And how exactly does it connect those dots? It uses part affinity fields, or paths. This right here is the absolute secret sauce of OpenPose. A path is essentially a 2D vector field. You can think of them as directional arrows that encodes not just where a limb is, but its physical orientation. If you're looking at a crowded room, paths are the reason the algorithm correctly associates my left elbow to my left shoulder, instead of accidentally attaching my arm to the shoulder of the person standing right next to me. It is a totally brilliant representation that solves the multi-person grouping problem without needing those clunky bounding boxes. Finally, this brings us to the modern pinnacle of this technology, HRNet, which stands for High Resolution Net. Now, while the stacked hourglass module we talked about earlier was definitely revolutionary, the encoding and decoding process still resulted in some spatial information getting lost when it downsampled. HRNet solves this subtle blurring issue in a really clever way by never downsampling the primary image in the first place. It maintains the full resolution throughout the entire network using parallel multi-resolution branches. It fuses the context from the lower resolutions, but without ever sacrificing the pristine, high-resolution spatial precision of the original input. Pretty amazing, right? As we wrap up this explainer, I want to leave you with one final thought. We have moved from brittle mathematical springs that broke the second an arm was hidden, all the way to neural networks that maintain the full, high-resolution reality of our every microscopic movement, even in dense crowds. With this technology scaling from 2D coordinates into rich, real-time 3D depth, what does the future of tracking human structure mean for our lives? Whether it's crafting perfectly immersive virtual reality avatars or ensuring an autonomous vehicle can read the subtle body language of a child on the sidewalk, the way machines understand our physical structure is going to fundamentally reshape how we interact with technology. Thanks so much for joining me on this deep dive, and keep your eyes open to how AI is learning to see the world.